talking about C, sort of reviewing some things that maybe you've learned in the past in preparation for Cash Lab, which is coming up. And then any extra time we have after we do that, we'll talk about Attack Lab some more. Okay. So Attack Lab is due this Thursday. You should start now if you have not started yet. And then once Attack Lab is due, Cash Lab will come out. Cash Lab is your next lab. So a C review. Okay, some warnings about C. That is the language that you'll be programming the rest of the labs in. The rest of the labs are actually writing code rather than just playing around in GDB and sort of doing the things you've done so far. It's possible to write bad code in C. Please don't. It will be style graded, and you need to watch out for certain behaviors that C has to make sure that your code is well written. So watch out for things like implicit casting. When you do integer comparisons in C and something is unsigned and something is signed, it casts everything to unsigned. Or if you do something with floats and ints, it'll cast the ints to floats before it does the arithmetic operation. And this just happens. You don't have to put the cast in here. It'll do it automatically. And that can sometimes cause behavior that you're not expecting. So watch out. Watch out for what types you're using in combination with each other. Implicit casting can cause problems. Watch out for undefined behavior. There's certain things you can do in C where the result is undefined. If you use memory that's not allocated, for instance, you don't know what its contents are. It could be anything. So you should make sure that you initialize your memory before you use it. Other such things can happen that would be undefined. Shifting by more than 32, that's undefined. So you should watch out for that. And if you didn't cover that, if you didn't take 122 and you're not sure about what the different undefined behaviors in C are, you should consult your copy of K&R, the second book that we recommend along with the textbook by the professors, because that book gives you the official standard of what different things in C mean and what different things in C don't have defined meaning. That tells you everything about what you can be guaranteed that the compiler will implement. You should watch out for memory leaks. So if you're allocating memory in C with malloc, you should remember that you have to free it before your program finishes, because if you have a program that never frees its memory and it runs for a long time, it will just consume more and more and more, and that is undesired behavior and can cause your program to crash eventually. You should watch out whenever you're using macros or pointer arithmetic. Sometimes those will be necessary, particularly malloc lab. You'll actually be wanting to use both of those to some extent. And they both have somewhat quirky behavior sometimes, where you have to be very careful about what you're doing because they can easily go wrong. And of course, K&R, that's the C standard version 2.0. That's the book we recommend. It's on the website. The full title is the official reference on how things behave in C. That is the standard that is implemented by every real C compiler, and it gives you all of the things that you're guaranteed about the language and also gives you the things that you're not guaranteed. So you should consult that anytime you are unsure about what the exact specification is of what something will do. Okay, so what we have here, we have some puzzles. So these are sort of a review of things that can go wrong in C. So each of these puzzles has something wrong with it. There's something where what you expect to happen if you don't know about C isn't what actually happens. So we're going to sort of go through them and see if we can figure them all out. So here's the first one. This is pretty simple. We take an unsigned int, and we do a comparison and return based on that comparison. Does anyone know what's wrong with this?
This will always return 0.
-1 will get passed implicitly to unsigned, which is 0x, FFF, whatever. So maximum unsigned integer, and nothing's larger than that.
Right, yeah, so that's the correct answer. So this one is wrong because you're comparing an unsigned int with a signed int, and the rule for that is that everything gets cast to unsigned. And we remember from our 2's complement arithmetic that -1 corresponds to the bit pattern of all 1s, which in an unsigned int would be maxint. So we're checking if u is greater than maxint, and that's always going to be false. So this actually always returns 0, which probably isn't the intended behavior, because why would we put that comparison in if that's what we actually wanted? So that's bad. Okay, that's that one. Here is another one, okay? So here we're mallocing some memory, and then we're doing some stuff with it in a for loop. Does anyone see something that could go wrong with this one?
Could be dividing by 0.
So you could be dividing by 0. Are you guaranteed to be dividing by 0? No. Right. So this one, what we did is we malloced some memory, and without actually initializing it, we just went off and started using it. And we happened to use it in a division. So this memory, it might contain zeros, in which case we would divide by 0 somewhere while doing this. But maybe it's all non-zero, in which case we wouldn't divide by 0. So this code actually is undefined in what it will do. It's undefined behavior in that maybe we'll raise a sig FPE from the dividing by 0, which would normally cause your program to crash unless you've handled it in some way. Or we might actually successfully return 0. So that is a problem. We don't know what main is actually going to do. It could do different things in different runs depending on the contents of that memory. So we always have to initialize memory that we get back from malloc to something before we use it, before we use its contents, because it could be anything. And you'll understand why it could be anything once you implement malloc lab. You'll see why there could be anything in it, because you'll be writing your own malloc and it will have that same behavior. Okay, that's good. Okay, here is another one. So let's see. So it looks like we're allocating a buffer and then copying a string into it and then printing the string. Can someone see what is wrong with what we're doing here? Be someone else, yeah, in the back. Right, yeah, so when we copy the string over, there's going to be the null byte at the end, right? Every string is terminated with a null byte. But the buffer we've allocated is only big enough to contain the string without the null byte. That's the size of the buffer we've allocated. So when we copy the string over, we're actually copying into a buffer that's 1 too small for what we're putting in it. So that means that we're actually going to overflow by 1 byte and write 1 byte outside of our buffer with this null character. And if that's something important, if that's some other piece of memory that our program uses, we've just corrupted things in a way that could change, what's going on.
One extra byte that will extend beyond it would be the null character.
It would be a null character, yeah. So we're writing a byte with value 0 into the character 1 past our array. And that's bad. We don't want to do that. So that, in this program, we don't actually really do anything with that memory, but maybe that's even memory that's inaccessible and will take fault because we went outside the bounds of what we're allowed to use. It's undefined to write to memory that you don't have allocated. Okay, so that's that one. Here's another one. Okay, so now we're using some structs. So hopefully you remember structs. It's a way to define your own collection of types. And here, what are we doing? We're making a node. Yeah, we're mallocating some space for a node and then putting some stuff in it. So can anyone see what we messed up in this one? I want someone who hasn't answered one yet. Yeah. You didn't free. Oh yeah, we didn't free it. That's true. That is an issue. There's actually another issue. That wasn't the issue that I meant to be there, but that is completely legitimate. What other issue is there in here? Potentially even worse than not freeing it. Okay, I guess you can. What? Node is a pointer, okay, and so why is that a problem? Right, yeah, so over here in the malloc, we do malloc size of node. So we say allocate enough space for something of size node. But we've typedefed node to be a pointer to this struct, not the size of the struct itself. So what we're really mallocing is enough space to hold a pointer. But then what we're using it for is to hold the contents of a struct. So if this struct is bigger than our pointer, we haven't allocated enough space. So if we're doing this on a 32-bit system, a pointer would only be 4 bytes. And so we'd allocate 4 bytes, but then we'd write 2 4-byte values there. And so we'd go 4 bytes beyond the amount of space that we had actually allocated. And that's a problem. So this could cause undefined behavior on a 32-bit system. And might actually be okay on a 64-bit system because they happen to line up and be the same sizes. And so that would be even more confusing if you're running it on different computers. And on some computers it works, and on other computers it sometimes fails. That would be annoying. That's the sort of thing that can happen in C, though. So that's why we need to watch out for these. So yeah, that's exactly what's wrong with that one. And of course, we should have freed it at the end too before we returned. That was also an issue that we should have watched out for. Okay, so here's another one. So what are we doing in this one? It looks like we're writing some sort of function that duplicates a character into a string. Sort of we're trying to get a string of n copies of character C is the goal here. But what did we do wrong when we did this? This one's a bit tougher. Yeah?
The dupe array was initialized on the stack, so once the function returns, we no longer have access to it.
Right, yeah. So the issue here is that we allocate this array called dupe as a local variable in this function that we wrote, which means that it's stack allocated. We allocate this n plus 1 space on the stack frame of this function call. But then at the end, what we do is we take its contents and we say, take this char pointer and point it to that same memory location, and then we return. And so when we return, you should have seen this in your, you've seen this in your TAC lab. When we return, that stack space, gets freed. The stack pointer comes up, but we still have a pointer to the spot down in the stack that was local memory for this function. And then the next function is going to come along and it's going to write something into that same stack space. And so our string that we think we have isn't actually going to necessarily stay the same sequence of characters. It's space that can be overwritten in the future because we've taken a local variable and sort of passed it out of the function. And it's no longer defined if it's passed outside like that. So the contents could become anything. It's just going to have random contents based on what other functions write to that same space. And that's bad because that's completely undefined. Okay, very good. Any questions on that one? That one was a bit trickier. Do you see how that's working? Okay. So now we have this one. So here, okay, so now we've introduced macros, everyone's favorite feature of C. What's wrong with this use of macros here? And the idea is that these two definitions of is greater are supposed to behave the same way. The order of operations. Okay, so yeah, so what do you think is going to go wrong?
So is greater, the capital is greater.
Uh-huh.
0 will be replaced with 1 greater than 0 plus 1.
Yeah, right.
It'll leave out with the 0 plus
Evaluate the 0 plus 1. Is it going to evaluate the 0 plus 1 first? That's the right idea. Yeah, that's the right idea, is that a macro is just a text substitution. So all a macro does, it literally just says, anytime I see a use of this macro, so in this case it's greater 1, 0, replace it with the contents of the macro. So it's actually going to take that part where it says is greater 1, 0, and replace this with the literal text a greater than b, where a is 1 and b is 0. And so what you end up getting is 1 greater than 0 plus 1. And since, so that's not in parentheses, so the order of operations, exactly. The order of operations is going to put 0 plus 1 first, and then we're going to do 1 greater than 1, and we get 0. But really what we wanted to do was 1 greater than 0 first, and then plus 1. So whenever you're using macros, you have to worry about the fact that it's literally going to just substitute that text straight into the program. And if it's substituted in something that will cause the order of operations to change because of what's next to it, then you might get unexpected behavior. And so, typically the way you deal with that is you just always wrap macros in parentheses to force them to stay contained. What does inline? Oh, inline is a special keyword that what it means is when it compiles it, rather than compiling it to a function call to this function, it's actually going to put the body of the function into the program at every place where it's called. So it sort of just copies the body of the function to the program everywhere, which makes, for small functions, makes things faster because you don't have to deal with jumping to the function definition and back every time. It's a similar idea to the macro, except that it's a compile time change versus a preprocessor text substitution before the compiler gets it. Okay, so everyone understand that one, the order of operations issue, because we didn't put parentheses around a macro. Okay. Good job. Okay, so and we've got this one. So here we've got another macro, and now we're doing some pointer arithmetic with it. This is starting to look similar to the sort of thing you will be seeing in Malloc Lab once we get there. Can anyone see what goes wrong with this one? And the next byte function is supposed to do what you would expect. It's supposed to give you the address of the next byte after the address you give it. Yeah?
You do the pointer arithmetic before performing the cast pair car pointer. So you're actually going to be looking, because of that you have a void pointer, so you can't perform pointer arithmetic on a void pointer. Is it going to complain? Well, I guess if the next byte macro is getting cast to void, in this case it's just going to complain. He's going to have a plus 1 and a1 is an int pointer. So you're actually adding 4 before casting the car pointer.
Okay, yeah. So that's the right idea. Is what we're doing here. So we're trying to use pointer arithmetic to get to the next byte. Now the way pointer arithmetic works is it depends on the size of the thing you're performing pointer arithmetic on. So when you add 1 to a pointer, it increments that pointer by the size of that type. So when you have a char is just 1 byte. And so you do pointer arithmetic on a char pointer, plus 1 just moves you by 1 byte. But if you're doing it on an int, which has length 4, then it moves you by 4 bytes. So it's sort of, if you had these things all in a row in memory, it would get you to the start of the next one by adding 1 to the pointer, is what it does. But what we've done here in this macro is, rather than casting a to a char star and then adding 1, so turn this pointer to a char pointer and then get me the next byte, just increment by 1, we've added 1 and then done the cast. So what that means is that when we add 1, the amount we add is going to depend on the type of the thing we've passed in. So we've passed in things of 2 different types, and they're different sizes, and neither of them have size equal to 1 byte. So we end up getting pointers to things that aren't just the next byte, because we add 4 to the int, and we add 8 to the long, before we actually cast to a char star, and then immediately after we cast it to a void star. And so we don't end up 1 byte after. So do you see how, so the solution to this would be to move this char star into here right before the A. So it'd end up being char star A plus 1. Do the cast before you do the plus. So you'd have to rearrange the parentheses. Does everyone see how that went wrong, how it didn't get its next byte, and how we'd fix that? Yes? Okay. So this one in particular is something that you should be solid on by the time you get to Malak Lab, because you'll be doing these sort of manipulations. And if you have a bug like this, then things will go terribly wrong, and it can be confusing why. Yes? I think the difference is that a long is guaranteed to be 8 bytes, whereas a long is potentially 4 bytes, depending on your system configuration. You can check K and R, but there's interesting things about which types are actually guaranteed to be which sizes. A long, I believe that a long is it's guaranteed to be at least as long as an int, but it might not actually be longer than an int. Similarly, a short is no longer than an int, but it might not actually be shorter than an int. A character is guaranteed to be 1 byte. We've got that one at least. It's in K and R for sure. You can check if you want to know the details. Okay, so those were the puzzles. Good job, you solved all of them. If any of you had trouble with those puzzles, if you think that those were really confusing, you would have never figured out a particular one on your own. We are having a sort of a C review, so sort of like we had the Linux review earlier this year. We're having a C review this Saturday. It's going to be sometime in the afternoon, probably around 2 o'clock. We don't have the room yet, so we'll announce the exact room and time once we have that confirmed. But it will be a good place to learn, to review all of these things, or learn them if there's things in there that you didn't learn in a previous class, if you felt that those exercises were difficult. So based on how you felt about those exercises, you can decide if the C workshop might be something that would be useful for you or not. We'll talk about those things in the slides: structs, pointers, standard library, all the different fun stuff you get in C. The details should be emailed out to you once we have them confirmed, which will be sometime soon. A couple other things about C. So C has a standard library. It's the stdlib header file. The way you get it in your program is you just include this line, #include standard library.h. This will get you access to all of the standard library functions. You should use it anytime you need a function that is implemented in the standard library, which will be probably all of the labs. You don't want to rewrite code that already exists. There's no point in rewriting these library functions, because you might not be able to write a version that has as many features, or you might write a version that has a bug in it or something, and that would be annoying. These standard library functions work. And if you want to know more about any of these, they all have man pages. So you can just type man and the name of the function, and it will tell you all kinds of great things about it. Tell you how to use it. It'll tell you, what arguments it expects, what their types are, and then a description of exactly what it does, what it puts out, and what the different return values mean. So, any questions about the standard library? It's also in K and R. There's some documentation about the different things you can expect to be in there. Another thing about C is robustness. So, we saw in those examples, a lot of those example problems had undefined behavior. And one of the frequent results of undefined behavior is that your program will crash. Because, either, you've divided by 0, or you've corrupted some memory and then something else goes in expecting it to be something valid and it's completely different. It usually will result in eventually the program crashes. if it's anything that's running for very long. So that's bad. You want to avoid making bad things, so you want to avoid writing code that crashes. So you want to avoid writing code with undefined behavior is one way to do that. But another thing you also want to do is you need to check every time you make a system call. So you'll be using different system functions. Malloc is one of them that is supposed to give you back a pointer to memory. But what if it gives you back null? That's a pointer, and malloc might give you back null if there's no memory for it to give. And then what do? You don't want to just go and use that memory as if it's valid, because you'll be dereferencing a null pointer, and that will cause your code to crash. And it will cause your code to crash potentially way down the line from when the system called actually failed, which would be difficult to debug. So what you want to do, anytime you make system calls, you should check the return code and make sure that you actually succeeded. The system calls, if you read the man pages, they'll usually have some sort of, if it returns -1 or something, that means something went wrong. And then you can catch that, and maybe the correct thing to do is to actually just cause the program to exit there, but at least you can give the error message of this went wrong, this is why I'm exiting right now, rather than crashing way down the line on something totally or seemingly unrelated. You should also check that you have valid input anytime you write a program that takes in things on the command line or some other type of input. If it's not checking to make sure that that input actually makes sense and just goes and uses nonsense input, that's bad because you're going to get some strange behavior that maybe you don't expect. For instance, if your program takes in an integer on the command line, maybe you need to check that it's non-negative before you use it, because it makes no sense to, maybe it's the size of something and it would make no sense for something to have a negative size in your program. And it might behave strangely or crash, and if it doesn't catch that, and you sort of print an error message to the user of no, don't do that. Some errors are actually recoverable, while others are not. When you get to Proxy Lab eventually, you'll see that certain things that are errors, like when your proxy is communicating with a client and that client just dies suddenly and unexpectedly, that creates an error because now all of a sudden you can't communicate with the client anymore. Your proxy should not crash because of that. Your proxy should not crash because it was serving requests to someone who unplugged their computer halfway through the session. The proxy itself should keep going, and so you should be able to recover from that error. Other things, like if the proxy itself segfaults, you can't really recover from that. It probably means you made a mistake in writing the proxy, but it's an unrecoverable error. So you'll see more of that then. And of course, free memory that you allocate. If you have a memory leak and your program is running for any significant amount of time, it will eventually crash, because it will use up all the memory and then it will crash. You'll see that also in Proxy Lab is when you'll see that, because the idea is that the proxy should keep running forever unless you turn it off. Nothing should your proxy should not stop unless someone explicitly decides that it's time for it to stop. And if we see memory leaks, that's something that will cost you style points, even if they don't cause a correctness issue on the autograder. So, another thing about robustness, so we have wrapper functions for the different system calls that you'll be using. They're the same name as the underlying system call, except with the first letter is capitalized rather than lowercase. And what they'll do is they'll, sort of somewhat gracefully terminate the program if there's an error. So, if the malloc comes back and there is no memory to be allocated, it will tell you that and just close the program immediately. That's useful if that's actually what you want it to do. That's not always what you want it to do. Sometimes you actually want to try to handle the error in some way and keep going. So these are not something that you would use all the time, but they are very useful if the desired behavior is when something goes wrong, then you just stop, rather than continuing on with some sort of undefined behavior. And you'll see the files with those when we have those assignments. You'll get the source code for all of that. Another useful thing in C is the getopt function. So you should check the man page for all of the details of this. But getopt will be useful to you. You'll be using it even in Cache Lab to be able to get arguments off the command line into your program. Because that can, that's sort of a tricky but boring thing to do correctly, because users can put in anything, they can put them in different orders. And how do you say I want these flags and these flags take these things, and tell me if I actually got something valid, and otherwise complain to the user that they did it wrong. Getopt will tell you how to do this. Getopt will be able to do this for you. Read the man page on exactly how to. Don't try writing your own command line parsing code. It's difficult and not very interesting. So style points. When you do start writing C, we will be reading your code for style. There is a style guideline on the website at that address, and you should read it if you haven't read it. And it probably wouldn't be a bad idea to read it again in between finishing your lab and submitting it, just to double check that the things you did actually match that style guideline. There's some macros in here if you want your text editors to automatically highlight lines that are too long. You don't need to use that. That's just optional if you're interested in being able to do that. See, you can also view your annotated code on Autolab. That's another good way to actually, that's how you'll see your feedback. Also, viewing your code on Autolab is a good way to see if it's too long, because if it's too long, it'll wrap the line around on Autolab. So you can scroll down the side with all the numbers, and if you ever see a break in the numbers, then that's because it wrapped one of the lines around because it was too long. See, GDB, yeah, so you've used GDB before, hopefully. Hopefully you all have used that for Bomb Lab and Attack Lab. It's very useful. Now that you actually have source code, you can try debugging with the source code available to you, and that's sort of a different experience, because now you actually get to see the line of the function that you wrote executing alongside the behavior. And there's ways to do this with the different layout options. So you can try that out. Here's a picture of a screenshot of a section of GDB with the source code available. So you can actually see, the assembly that's happening, but also right next to it, the line of the source code that assembly came from as something is going on. See, so Valgrind. Valgrind is a tool that you'll be using if you want to find memory leaks. So if you took 122, you should be familiar with Valgrind. You can also check the man page for it if you want to learn more about it. But what it will tell you is it'll tell you, at the time the program exited, there is this much memory that had been allocated that was not freed. It will tell you, if you happen to free the same piece of memory twice, that's undefined behavior. You should never, if you malloc once, you free exactly once. You don't free 0 times, you don't free twice. And it will tell you if you accidentally free something twice. It'll tell you sometimes if you're corrupting memory in some way, can sometimes help you find out what's going wrong with that. And if you compile your program with the -G flag, which puts all of the debugging information in it, then Valgrind will even give you line numbers where things go wrong, which is very useful. Version control. If you're familiar with version control, you might find it useful to use. If you've never used a version control system before, you don't need to learn how to use one for this class. It's not something that's necessary or required. It would be useful for you to possibly make regular submissions to Autolab, just so that you have a backup of recent work if something goes wrong, because you can download any of those submissions and see what your code looked like then. You're also guaranteed that you've got at least that much checkpointed there where you can't lose it if you accidentally delete a file or something. GCC, you've used GCC. That's the compiler for C that you're using. We'll give you instructions for particular labs in each handout, and you can man GCC if you want to learn all about the different things that GCC can do. Man pages are your friend. That's sort of the answer to a lot of how do I use this, what does it do? Check the man page. That's what those are for. Labs will come with a makefile. Don't modify the makefile, because if you make it do something different than when you submit to Autolab, it's not going to be doing the same thing. You'll have to write your own for Proxy Lab. That's the exception. You get to modify it from a blank file into whatever you want. The examples for syntax will be found in previous labs. So once you get to Proxy Lab, you can kind of figure out how to write it based on looking back what they did before. And we can talk about that more as that gets closer, the contents of a makefile. But to run a makefile, all you do is type make. Make will find the makefile in that directory, and it will execute its contents, which typically is to compile your code. It's an easy way to automate commands and stuff. Okay, so any questions about C and the different tools that we did a quick overview of? No questions? You're all experts? Excellent. If you're not an expert, you can, of course, come to the C workshop, and you'll be an expert by the time you leave. That's happening on Saturday. So what we're going to do with our remaining time is we're going to sort of go back to Attack Lab. So we talked about Attack Lab last week, right? But a lot of you were at the TOC, and also it wasn't out yet. So it was sort of like I was talking about something, and you're like, oh, I don't know what's going on. This is a handout that I haven't read in a lab I haven't worked with. So now that Attack Lab is actually out, we want to go back and just use the last 15 minutes to review some of the stuff that we talked about then. So are there any specific questions or troubles with using hex to raw, getting your string into the target, those sort of things that anyone has been having that they would like for me to go over? Yeah.
When it reads an injected string, is it reading Little Endian or is it reading?
So when it reads an injected string, so what's happening? So you give it, you have your sequence of bytes in a file, and you run it through hex to raw, right? And what's happening is that when that runs in the program, the buffer overflow, it's going to read that string, and it's going to put those bytes into the buffer in that order. Okay? So it's going to put the bytes into the buffer in the order that they are in your string. From the lowest address will be the first byte, and the highest address will be the last byte of that string. And then, that's the order that the system is going to see them in. So if you have an integer constant in there, then you should arrange the integer constant in little endian order in your attack string before you pass it in, because that's what the system is expecting. Does that answer your question?
Okay, so it would be the same as with addresses. You would also arrange.
Right. Yeah. Addresses or constants should be arranged in little endian order in your attack string.
I see, but commands are ordered the opposite.
But commands will be ordered, in the order that the same order that object dump puts them out in. Right. Yeah. Yeah.
So in the buffer, I guess my question is, for the addresses, they're 64 bytes long.
So well, not 64 bytes. 64 bits. Yeah.
64 bits, sorry.
That'd be huge.
So how does it arrange it in the stack, I guess? Is it 16, or is it 4, I guess would it be 8 bytes, or 16 bytes per, or 32 bytes per row?
It would
Row?
32 bytes per what?
I'm just curious how it's arranged, because sometimes the address we're given to an instruction doesn't fill all 64 bits.
Doesn't fill all 64 bits.
So
Yeah,
so you have to put filler in, or
So anything that GCC and object dump outputs is fine as it is. Like if you run a piece of assembly through GCC and object dump, the byte code it puts out is byte code that the computer knows what to do with. In terms of alignment, you should worry about making sure that you're aligning things to the right size. So an address or a 64 bit constant of any sort should be 8 byte aligned. If you want to make sure that you're not going to have weird overlap issues. Any other questions? People are understanding how to go about the lab? Yes? Okay. Let's see, is there anything interesting? So a couple, I guess, to address some of the address some of the questions that we had over email from multiple people. So a lot of the questions were about actually using hex to raw. So we have here in the handout these different ways to use hex to raw. Oops. This is page 12 of the handout. So, when you're actually going about it, if you want to, say, pass your string into GDB to debug, then you have this flag -I. So say you had a string. So I have a target here, and was foo one of my strings from last week? Yeah, foo is my string from last week. And I can say hex to raw gets foo and outputs foo.raw. And so that actually gives me the raw string. In a file. And then if I want to actually pass that into the target in GDB, then when I open up GDB on my target, I can do a run with -I and give it that raw string that I created. And so here, nothing happened because that string wasn't very interesting. Also, if I want to just pass it on the command line, we see that we've got, this command, we can do it all in one step on the command line. Where we do ctarget. And we can give it this foo.raw here on the command line without ever going to GDB the same way. Or we can use one of these versions where we pipe it through, so we can then, without ever actually putting it into a file, run it through with pipes. And another thing that might be useful to you is WC. So that gives you a word count and character counts for a program. So what this told me is that it's one line, one non-empty line, and that has 15 characters on it. So if you wanted to know how many bytes were in your exploit string, if you were worried that maybe you miscounted, and you have a byte fewer than you were supposed to or a byte more, WC is a way to get information about the bytes. In your file, you can read the man page to see what it does exactly. Or you can actually even, here's an interesting thing. You can do a word count with -L. That tells you the maximum line length. If you want to make sure that your C files for Cache Lab don't have any lines more than 80 characters, there's a great way to check that none of the lines are too long. If that comes up as more than 80 on your C file, then you know that somewhere you need to split a line into two. Yeah, question?
I have a question about the ROP attack.
The ROP attacks, yeah, okay.
So I didn't get the format that they're supposed to go in. Is it supposed to be, so you get the address of the gadgets, I guess?
Right.
Do you just put a string of all the gadgets addresses typed in? Or?
Right, yeah. So what's happening in the ROP attack? So you have your stack here. You've got a bunch of addresses on it. And here's the address of gadget 1, gadget 2. And so, the way the attack works is that this is some pointer to some gadget code. And this gadget code ends in a ret. So what happens is when you execute this code here, so when you get your program to jump to this, it executes the gadget code and then it executes a ret, which causes you to pop the next thing off the stack and jump to that location.
So would you put as that gadget, the address of that gadget? Is that what
So right, exactly. So the thing that is popping off is the address of the next instruction to go to. So this is, address of gadget 2, address of, using the sort of C address of operator.
And I'm also confused by how you would, so if you had a store like a cookie or something,
Mm-hmm.
how do you, because all the gadgets I saw, they were taking something from a register and moving it to another register or dealing with registers.
Okay.
How do you actually put something into a register?
So the way you take something into a register would, if you happen to have a constant move into that register, that's the right constant, that would be great. But what you'll probably want to look at is if there's ways to pop things into registers, because that's how you can get something off of the stack into a register. And so if you look in the handout, we give you, the different byte codes for all of the pop instructions. So if you can find a gadget that contains one of these pops, and then you can line up something on the stack that you want to get into a register in the right slot on the stack, then one of your gadgets can actually pop something off the stack into a register, and then the other gadgets can move it around into whichever register you want it to ultimately end up in. Other questions? Yes?
It seems like after you've injected some code, its GDB can't quite step through. Like GDB seems to get kind of confused. And
So-
it'll just crash.
Right, okay, yeah. So what you're probably, are you doing something where you're in like this layout mode where you view the assembly right? So when you get to your injected code, the thing is with the injected code is that it doesn't belong to any of the original functions of the file. Like it's just this, you're ending up with these weird instructions. GDB does not know how to display this window when you're in that injected code. So in order to make it work, it gives you some message about, like code not in function, something. The problem is not that the executable can't run, it's that GDB doesn't know how to display this window, so you have to turn that window off whenever you're inside your injected code. And then you can sort of just, examine, with print and examine, there's ones that format things as instructions, so you can actually see what the instructions are at your pointer, even though you don't have that window open. You can still get the assembly to print.
How
Yeah.
do you get the assembly window to turn off?
I think maybe if it's layout not a thing. No. You might actually have to just quit GDB and open it back up.
I saw layout none on like Stack Overflow. I kept trying to do it, and it wasn't doing anything. I ended up using Control X, Control A.
Control X, Control A. Yeah, Control X, Control A. Emacs style syntax. Which isn't surprising. GDB and Emacs are both GNU projects. So. Other questions? That was a good one. I know a lot of people are having that issue. None? Okay, if there's no more questions, it's about time for today, so I will let you all go. Good luck with finishing your attack labs. And then Cache Lab will be out this week.